Recorded, it's rolling. It's Friday, November 14th. We're at the end of the interim. So here's top scientist for energy. So awesome job. You made top scientist. Yeah, got lots of top scientists. You guys are doing great. Oh, also, here I got this flyer for a math competition. That's December 5th. During the school day in the gym. I don't know exactly how this works out, but if you want to sign up, I did post the link also on Google Classroom, so that's there. And yeah, if you're interested in that, it's like a math competition, and it's Friday, December 5th. All right, so AP, you guys know you have an AP classroom. Do by the time you guys show up to school on Monday, so that we can go over the answers on Monday, right? Yeah, I think you guys will be able to do good on those. I did go over these basic momentum puzzles with you guys, 1 through 11. A lot of you guys have already turned this in, but if you haven't, then I'm going to put this into the grade book this weekend. Okay. I did put the college physics textbooks puzzles in your hands, so we can cover some of these next week. But that's just be next week thing. Of course, if you want to read these ahead of time or have some extra puzzles, then got some extras to work on. All right, but main thing today is going to be this collisions lab. And so, any questions so far? We're going to collisions lab. All right. So yesterday you guys did an elastic collisions lab, which was where these two carts would fly and stick together. And what you should have seen, or something pretty close, the numbers, how they should bear out, is that the momentum should be conserved. So if you add up all the mass times velocity before the collision, and then do the sum of the mass times the final velocity after collision, it should be pretty close. Right? And I was looking at you guys' numbers, and it was fairly close. Right? Sometimes it went down a little bit, which might be expected because there was a little friction. Right? Sometimes it went up a little bit. Maybe there was some kind of measurement error or something. Right? Yeah. But it should be pretty close, these two. Right? But what did you guys notice for kinetic energy? What happened?
Oh, that one definitely.
Yeah, it should definitely go down. There definitely be less kinetic energy in the system post collision compared to pre. And remember momentum pre here because I got this question to you yesterday. Remember, so before collision you had mass A, velocity A plus mass B, velocity B. And one trick is you could start one cart at rest, in which case that would simplify it because zero momentum from that part. But then post collision, the momentum is the sum of the masses times post collision velocity. Right, that's how you get that. Right? It is a similar thing for kinetic energy, but kinetic energy is 1/2 mv squared. So you add up all the 1/2 mv squared before, all the 1/2 mv squared after, and that was yesterday. Now today is going to be a little trickier because general collisions. What I want you guys to do is have the carts bounce off each other. Now, there are magnets already embedded in the cart, so they'll naturally bounce off each other. In fact, they bounce off really nice. It's very close to the elastic end of the spectrum. Actually, I did link this up there yesterday. So you can either take the bar magnets off, because these bar magnets you take on here, or if you want to, you could just flip one of them, so they'll repel even better off each other. Now, because that magnetic force between the two carts is just internal to the two cart system, so it doesn't actually mess up any of this at all. Right? It's just an internal force, not an external force of the two cart system. Now, the reason this one's a little trickier is because post collision, you definitely have two separate carts, each doing their own thing. So you have to capture two separate velocities post collision. Okay, you guys see that? Okay. Now, pre collision, there's also two velocities to record. Again, you could have one of these set to 0, that could simplify it. But even if you do that, if one of these is 0, you still have to capture 3 other velocities, 1 pre and 2 post. You guys think you can coordinate the speed gates to capture those? Right. So a little trickier than yesterday. You guys might have to have a little bit more teamwork than yesterday. However you do that. Okay. But the calculations are pretty similar to yesterday. So you got all the MV before collision, all the MV after collision. Right. That signal needs the sum of. Okay. And then all the 1/2 mv squared before and all the 1/2 mv squared afterwards. Okay. Now, do you guys think that momentum should still be conserved before and after each collision? Yeah. So like this box and this box should be pretty close to the same number. If this is like 1.6, this should be about 1.6, maybe 1.5, something like that. Now, since these carts are bouncing off each other pretty elastically, what do you expect to see in terms of kinetic energy before and after? Yeah, mathematically, ideally, textbook value should be the same value. Right? And then realistically, there's a little bit of friction here. Like if you give us a small push, it'll probably stop before it even reaches the end of that 2-meter long track. Right? So it might go down a tiny bit, but it should be pretty close, or a lot closer today than it was yesterday. Right? These terms. Okay. You guys get that? Okay, so today's just an exploratory lab like it was yesterday. So if you want to change out the masses, you can change out the masses just by very simply doing something like that. Okay, 0.5 kilograms here, 1 kilogram here. Boom, that's 1.5. Or if you want to change how hard you push it to change the initial speed, right? So you can vary things. Right? So it's just exploratory, just try different sets of values and see how they work out. Right. So go ahead. You guys can turn this into the grade tray at the end of class. All right.